I'd like to start by thanking the IPDLN for the opportunity to present and to the committee for bringing together this conference during challenging times. I'd like to share with you results from a study that we conducted that looked at the association between ultraviolet radiation in early life and risk of type 1 diabetes in childhood. We've come a really long way in our treatment of type 1 diabetes, and yet its prevention still eludes us. Multiple studies, however, have now confirmed that type 1 diabetes risk can be identified prior to symptomatic disease through the presence of 2 or more diabetes-related autoantibodies. Importantly, these antibodies can be detected from as early as 3 months, with a peak between 9 and 24 months of age. The lifetime risk of developing symptomatic type 1 diabetes approaches 100% once 2 or more of these islet autoantibodies are detected in at-risk children. The ability now to predict type 1 diabetes risk through screening prior to symptomatic disease has really heightened interest in identifying interventions that may delay disease progression, but it's also really put the spotlight on the gestation period in the first year of life as important windows of opportunity to prevent islet autoimmunity and ultimately type 1 diabetes. UVR exposure has become of increasing interest over the past decade in relation to autoimmune diseases because of its immunoregulatory actions. Recent intervention studies of other autoimmune diseases, such as multiple sclerosis and more recently eczema, have demonstrated an association between higher UVR exposure and lower incidence of disease. It's independent of vitamin D. And there's 3 notable observations. It gives us hope that high UVR exposure may lower the incidence of type 1 diabetes also. So firstly, the incidence of type 1 diabetes has increased in the past decade at a rate too great to be solely attributed to change in genetic risk. And this is further supported by the fact that we see fewer children presenting with type 1 diabetes with the known higher risk HLA genotypes. So this suggests a significant role for environmental influences. Secondly, we see that the incidence of type 1 diabetes generally increases with distance from the equator or with latitude. And then finally, we see that the disease onset generally peaks in winter months when compared with other months of the year. And so one environmental factor that varies by both latitude and season is ultraviolet radiation. So UVR can be measured in a number of ways and with varying levels of accuracy. So long-term exposure can be measured by silicon casts at back of hand skin to objectively measure actinic damage. And short-term exposure is measured by electronic dosimeters, sun behaviour diaries, or blood 25-hydroxyvitamin D, also known as 25-OHD, which is a major circulating metabolite of vitamin D. And that reflects both sun exposure as well as dietary intake of vitamin D. For many diseases, though, we're actually interested in the UVR exposure of particular life stages, and that was the case for our study of type 1 diabetes, and this is inherently more difficult to measure. And studies have traditionally relied on self-reported past sun exposure, and in some instances requiring a recall over decades in the past, which is obviously unreliable and/or inaccurate. More recently, we've seen that NASA satellite data of erythemal UV dose is being used as a proxy for personal sun exposure. So erythemal UV dose are calculated using the UV irradiance that reaches the surface of the Earth, and then it's weighted by a model value of susceptibility of Caucasian skin to sunburn. So these data are date and geographically specific, so it provides a daily dose for each latitude and longitude throughout the world, thus providing a finer spatio-temporal scale than latitude, whilst also being able to account for seasonal changes. So these data are perfect for data linkage studies, enabling large-scale retrospective studies to be conducted in a cost-effective and efficient manner. So this is the UV measure that we decided on for our study. However, although erythemal UV dose is an objective measure, it doesn't measure an individual's true exposure. So that is, it doesn't take into account an individual's time in the sun or their sun protective behaviours, which obviously varies between individuals. So as a result, the first critical step for us was to establish the relationship between erythemal UV dose and serum 25-HG levels during pregnancy to assess whether the NASA measure that we were proposing to use was in fact a valid proxy for an individual's actual sun exposure. So we conducted a retrospective cross-sectional study of over 19,000 women aged 18 to 44 years who had their 25-OHD levels measured during pregnancy. The gestation of the women at the time of blood draw ranged from 0 to 41 weeks, and the location ranged from 10.5 to 34.5 degrees south latitude, and the sampling was equally distributed throughout the seasons. So we linked the midwives notification system, which is an administrative data set complete for over 99% of all births in Western Australia, with 25 OHD measurements from PathWest Laboratory, which is a statewide public pathology service that conducts over 80% of all the pathology tests in Western Australia. So in brief, we found that the NASA's measure of erythemal UV dose was a significant predictor of 25 OHD levels in pregnant women, and that a model only using administrative data was able to explain a similar proportion of variance to many of the cohort studies that have accounted for individual son behaviour. So the predictive model that we developed in this study was then used in our type 1 diabetes study, which I'll now move on to. We conducted a nested case control analysis within a cohort study using linked data from statewide administrative data sets. So cases included all children who were born in Western Australia between 1980 and 2014 with a diagnosis of type 1 diabetes before the age of 16 years. Our population-based controls were randomly selected from all live births in Western Australia from the midwives notification system at a ratio of 1 to 15, and they were matched on sex and date of birth. And our controls also needed to still be alive and not being diagnosed with type 1 diabetes at the date of diagnosis of their matched case. So our data for cases were obtained from the Western Australian Children's Diabetes Database, which is a prospective statewide registry, and that includes data for over 99% of all Western Australian children who are newly diagnosed with type 1 diabetes. We use the midwives notification system for our selection of our cases and controls, and it also provided us with perinatal data on all of our participants. As controls were selected on the basis of being alive at the age and date of diagnosis of their case, death registration data was also required to identify who to validly include and exclude from our pool of controls. The data linkage of these data sets was performed by the West Australian Data Linkage branch, and then we then sourced the NASA satellite UV data, and that was date and location specific for each individual. And we achieved that by using the date of conception, the date of birth, and the latitude and longitude of the residential postcode that was recorded at the date of birth on the midwives notification system. We also obtained data from the Australian Bureau of Statistics on social disadvantage and education and occupation, and that also was merged into the project dataset on postcode. So now moving on to our results. So cases were more likely to be Caucasian, born via caesarean section, be of younger gestational age at the time of birth, have a mother with diabetes prior to pregnancy, and reside in the Perth metropolitan area. We found no differences between the maternal age at the time of delivery, birth order, infant birth weight, APGAR score, or gestational diabetes between the two groups. Our analysis stratified by sex indicated a significant effect on UVR, on type 1 diabetes risk in boys, but not in girls. So as you can see in the table here, among girls, the total UVR dose was not associated with subsequent type 1 diabetes risk in any of the time periods that we investigated. However, among boys, mothers of boys, higher total UVR dose in the third trimester was associated with significantly lower risk. So when the third trimester total UVR dose was considered into quartiles, the risk of type 1 diabetes was 42% lower for the highest quarter compared with the lowest quarter. And then similarly, for the first year of life, the higher total UVR dose over the first 12 months of life was associated with significantly lower risk of type 1 diabetes among boys, and this effect was more pronounced for the first 3 months post-birth. So for every 100 kilojoule increase in the total UVR dose, the relative risk of type 1 diabetes among boys decreased by 29%. So in summary, these data show the association between higher ambient erythemal UV in the third trimester and first year of life, and subsequent decreased risk for type 1 diabetes in childhood among boys. And I'd just like to finish by acknowledging all of those people that were involved in the study. Thank you so much for listening.